Okay, let's talk about reactions in solution. There are some similarities to some of the calculations we did in chapter 3 with the theoretical yields and how much product or how much reactant you need, but we're going to have a different way of getting at moles. What we have is molarity and volume in liters, but fortunately molarity times volume in liters is still moles, so I can still relate the reactants and products using the stoichiometric coefficients. And so the problem will work similarly, but not quite the same. I won't need molar masses for substances that are in solution. So in this case, we have an example. We want to know what volume of 0.5 molar barium chloride is required to completely react with 4.32 grams of sodium sulfate. So I'll need the molar mass of sodium sulfate, but I won't need the molar mass of barium chloride. But then the calculation will work the same. I still need a balanced reaction. Sodium sulfate plus barium chloride forms barium sulfate plus 2 sodium chlorides. All right, so let's look at this when we got 0.5 molar barium chloride, 4.32 grams of sodium sulfate, and we have the molar mass I calculated in advance. We're going to use this reaction to figure out what volume of this we need to neutralize all that. So since I know everything about the sodium sulfate, I will start with that. 4.32 grams of sodium sulfate. Then 1 mole sodium sulfate is going to be 142.05 grams of sodium sulfate. And then since the stoichiometry is 1:1, there's going to be 1 mole of sodium sulfate to 1 mole of barium chloride. Then I'm going to use my molarity to get the volume, 0.500 moles per 1 liter. So the moles cancel, those moles cancel, the grams cancel, and we're good to go. So we say we got 0.0608 liters of barium chloride solution, which turns out to be 60.8 milliliters of barium chloride solution, and that would be our answer. Let's look at titrations. It's an application of the reactions in solution type problem. Titrations are a method for determining the concentration of an unknown substance. So I need to know either the mass and molar mass of a solid that's in the flask that I dissolve, or I need to know the molarity and the volume of the other solution. It's going to require special glassware. We're going to need a burette to measure the dispensed liquid, accurate to 2 decimal places. If your substance is going into the flask is a liquid, then we'll need to pipette it in so we know the volume, again, to 2 decimal places. There's also an indicator. An indicator is a special color changing dye that indicates the end of a reaction. Phenolphthalein is the most common indicator in general chemistry. An acidic solution is colorless, and it's pink in alkaline solution. That is, once it gets a little basic, it's going to turn slightly pink. If you overshoot your titration, it'll turn dark pink, and that's a good indication you've overshot that titration. Here's a picture of what that would look like. There's the burette into the flask where you can measure how much stuff is going in. You turn the valve, let some go in, and you can see that that solution is barely pink. You can when you see it against the white background, that's a pretty good endpoint. If it's darker than that, you probably got an endpoint where you've overshot it a bit. So let's look at a concentration problem with a titration. So we got a molarity of a barium hydroxide solution. We want to know what that is. If we got 44.1 milliliters of a 0.103 molar hydrochloric acid solution reacting with 38.3 milliliters of the barium hydroxide solution. We have barium hydroxide reacting with 2 HCl's to form barium chloride and 2 waters. So what do I know? I know the concentration and the volume of the HCl, but I only know the volume of the barium hydroxide. And so I'm going to have to use the solution I know to get the solution that I don't know. All right, let's take a look at this problem. We got 44.1 milliliters HCl, 0.103 molar HCl. So we know both of those, but we only know the volume of the barium hydroxide. So we're going to use that to calculate the concentration of the solution we don't know. We still have our balanced chemical reaction here. Notice the 2-to-1 proportion. So we can't use the dilution formula. We'll start with the HCl, and we'll put it in liters. 0.0441 liters times our molarity, 0.103 moles of HCl to 1 liter. So the liters cancel, and we're left with moles of HCl. Then we're going to use the mole ratio, 2 moles HCl to 1 mole of barium hydroxide. And then at the end, we're just going to divide through by the volume, because moles divided by volume is going to be molarity. So divide by the volume in liters. So converting that to liters, 0.0383 liters. And then we're going to get 0.0559 molar barium hydroxide, and that would be your answer. All right, this problem uses the limiting reactant concept to figure out how much product would form and what's the limiting reactant, how much is left. So we're going to use calcium hydroxide plus 2 HCl forming calcium chloride and 2 waters. And we're going to have a chart that we're going to fill in that's in moles for the calcium hydroxide, the HCl, and the calcium chloride. We won't worry about water because the concentration of water in the aqueous solution is somewhat of a moot point. But we'll determine the limiting reactant, we'll determine the moles as the salt formed, and we'll determine the molarity of the moles and the molarity of the salt formed, and then we'll determine the molarity of the reagent in excess. That is what's left at the end of the reaction. We'll take each of those things. All right, so let's look at this particular problem. I've again copied down all the information. Here I have concentrations and volumes of both things, so I'm going to be a little bit more careful. So we want to determine the limiting reactant first. That was part A. And so we need to figure out the initial number of moles of each substance to begin with. So my initial moles calcium hydroxide is going to be 0.0550 liters of the calcium hydroxide solution from up here times 0.0500 molar, which is going to give me 0.00275 molar, or moles. So that is the initial amount up here. So 0.00275 units or moles all the way across. So then we just need it for the moles of the HCl. These are again initial amounts. 0.0203 liters times 0.246 moles per liter, which will give me 0.00499 moles. And so we're going to put that up here. 0.0499. Now, if you look at the stoichiometry, we can tell what the limiting reactant is because there's I would need twice as many moles of HCl compared to that. But if I take that and multiply by 2, I'm going to get over 0.5 because 250 would give me 5 there. But I've got a little bit less than that. So I can say my HCl is limiting, which means that, so this is part A, sort of a means to an end. HCl is limiting, which means I'm going to use all of that up and not end up with any left. So I'm kind of filling in the table as I go along. Now, I got to figure out how much of everything else. The coefficient there is 2, but there it is only 1. So if I divide that by 2 and rounding for sig figs, I'm going to get 0.00250. So I'm going to have just a little bit left, 0.00025. And then I don't start with any product, but I'm going to add the same amount because these coefficients are the same, 0.00250. So I'm ending with 0.00250 moles. Now let's go back and answer the questions. What's the moles of the salt form? We just calculated it. So B would be 0.00250 moles of calcium chloride. C is going to be the molarity of that salt form. So it's going to be calcium chloride. We're going to use that number of moles, 0.0250 moles. But now we have to divide by the total volume of the solution, which is going to be the 55 and the 20.3, which would be 70.3, or 0.0753 liters, or 0.0033 molar. And that's going to be your answer to part C. D, molarity of the reagent excess. Up here we see 0.00025. So we're going to use that. Concentration of the calcium hydroxide. And that's going to be 0.00025 moles divided by the same volume. So it's really factors of 10 in this particular case. It's going to be 0.0033 molar. And that's your answer. I realize this particular problem is a little bit more involved, but we in fact do get the answer with a little bit more effort than before.